Have you ever heard of a person who has 3 biological parents? Really? Can someone have 3 biological parents? This sounds mind-boggling, right? But today I'm going to tell you about a certain mitochondrial disease known as Leigh syndrome. Welcome to this episode of If You Don't Know, Now You Know. Each and every cell within your body contains numerous mitochondria or hundreds of mitochondria in their cytoplasm. Mitochondria has a DNA in a single circular chromosome that codes for 13 proteins, various RNA, and several regulatory enzymes. However, more than 90% of these mitochondrial proteins are coded by the nuclear gene. In short, it means that the nuclear DNA creates all but 13 of these proteins, which are coded for by the mitochondrial DNA. For practical purpose, we inherit all our mitochondria from the cytoplasm of the egg. Thus, mitochondrial DNA is only inherited from the mother. We never inherit mitochondria from our dad. So we owe our mothers a big one. We need to thank them for this. A cell has one nucleus and numerous mitochondria with their own DNA. Mitochondria uses a process called oxidative phosphorylation to generate their energy. This energy is used to aid various processes within the cell and within the body. That's the reason why they are called the powerhouse of the cell. Mitochondrial disorders may be due to mitochondrial DNA or nuclear DNA abnormalities. For example, deletions, duplication, and mutations. If mutations affect mitochondrial DNA, some might be healthy and some might be defective. It takes about 1,500 proteins for mitochondria to work properly. So a problem in these proteins may lead to disease or mitochondrial abnormalities or disorders. High energy tissues and organs, for example the heart, muscle tissue, and the brain, are particularly at high risk of malfunction due to mitochondrial DNA abnormalities. But any other tissue in the body can be affected, and this can occur at different times throughout life. Some inheritance patterns characterize abnormalities in the DNA mitochondria. Thus, all the offspring of the affected female are at risk, but no offspring of the affected male will be at risk or is at risk. Variability of clinical manifestation is the rule. These abnormalities mimic a broad range of disorders, which often makes a diagnosis very difficult. And variability may be due in part to variable mixture of inherited mutant and normal mitochondrial genome within the cell. Both male and female are equally affected with this type of conditions. Mitochondrial abnormalities may occur in many common disorders, such as some types of Parkinson's disease, which involve large mitochondrial deletions in cells of the basal ganglia. Other examples of mitochondrial disorders may include Mitochondria myopathy, Leber hereditary optic neuropathy, monoclonal epilepsy, and Leigh syndrome. Let's now shift our undivided attention to Leigh syndrome, which is the main topic of this presentation. Mutations in over 75 genes, both in mitochondrial DNA and nuclear DNA, may result to Leigh syndrome. Genes that are associated with the Leigh syndrome are involved in energy production in a process that we named earlier. We call it oxidative phosphorylation. 5 complex proteins are involved, each with several proteins, which are complex 1, complex 2, complex 3, complex 4, and complex 5. Distribution of complex 1, also known as NADH, ubiquinone oxidoreductase, is the most common or the most non-common cause of Leigh syndrome. The distribution of complex 4, also known as cytochrome oxidase, abbreviated as COX, COX, is also another common cause of Leigh syndrome. Approximately 15% of cases of Leigh syndrome. The most common mitochondrial DNA mutation in Leigh syndrome affects mitochondrial ATP6 gene, which provides instructions for making complex 5, also known as ATP synthase protein complex. Other gene mutations related to Leigh syndrome affects one or more oxidative phosphorylation protein complexes or additional steps that are involved in energy production. For example, Leigh syndrome can be caused by mutations in genes that are involved in formation of a pyruvate dehydrogenase complex or coenzyme Q10, both of which are involved in the process of energy production. Mutations in genes that are involved in replication of DNA of the mitochondria or involved in production of mitochondrial proteins can also disrupt the process of energy production. Although the exact mechanism is not known, but researchers believe that impaired oxidative phosphorylation can lead to cell death. This condition becomes apparent in the first year of life, and it affects at least 1 in 40,000 newborns. So it is characterized by psychomotor regression, which is loss in the mental and movement ability, and it typically results to death in 2 to 3 years, mostly due to respiratory failure. However, some few individuals may not develop symptoms until adulthood, or the symptoms may worsen slowly. Most symptoms that occur in this type of condition are dysphagia, which is inability to swallow, delayed milestones or failure to thrive, severe muscle and movement problems, hypotonia, which is a low muscle tone, dystonia, which is involuntary contraction of muscles, ataxia, problems with the balance and movement, peripheral neuropathy, loss of sensation and weakness in the limbs, ophthalmoparesis, weakness in muscles that move the eye. Then we have nystagmus, rapid involuntary movement of the eyes or muscles of the eyes. Then we have optic neuropathy, degeneration of the optic nerve. Some may develop hypertrophic cardiomyopathy, whereby the heart muscles harden, and this forces the heart to work even harder. Lactate may also build up and may be revealed in blood, urine, and cerebrospinal fluid. Signs and symptoms of this condition are characterized by lesions in the brain, and MRI may be used to reveal the characteristic lesions in certain areas of the brain. Such regions include the basal ganglia that helps control movement, the cerebellum that helps in coordination of movement and balance, the brainstem that connects the brain to the spinal cord and also controls functions such as swallowing and breathing, and even cardiovascular functions. So the question that we are left with, what can be done to manage Leigh syndrome? Treatment can be so difficult, but in some cases, this disease can be stopped before it is passed on. As we said earlier, all mitochondria are inherited from the mother. So if the mutation is in the mitochondrial DNA, it can be stopped or blocked. One approach that embryologists use is by combining the nuclear DNA from an affected egg cell with a mitochondrion or healthy mitochondrion from another healthy woman. The embryo will have nuclear DNA from the original mother and the original father, with a mitochondrial DNA from the egg donor. This has led to some people calling such potential infants three-parent baby, but I wouldn't call them a three-parent baby, bearing in mind the embryo had nuclear DNA from the original mother and the original father. This means that they will have traits of the original mother and father and not the egg donor. And also the egg donor has no legal rights over that child. This technique is still new, but it has been recently approved in the UK. And the last time embryologists tried to create a baby using DNA from 3 people was in 1990s. They injected mitochondrial DNA from an egg donor into another woman's egg cell, along with the sperm from the partner. 2 of the fetuses developed genetic disorders, and this technique was halted by the US FDA. The problem might have arisen from the fetus having 2 sources of mitochondria. In a certain article, Exclusive World's First Baby, born with the new 3-parent technique by Jessica Hamzlu, there was a mother who carried genes for Leigh syndrome. While she was healthy, Leigh syndrome was responsible for the death of her first 2 children. So the couple sought help from an embryologist called John Zhang with his team based at New Hope Fertility Center in New York City. There are a few ways that they would have used this technique. One approved in the UK is called pronuclear transfer, whereby it involves fertilization of the mother's egg and the donor's egg with the father's sperm. Before this fertilized eggs start dividing into early stages of embryology, each nucleus is removed and the donor's egg is discarded, replaced by one from the original mother's fertilized egg. This technique wasn't appropriate for the couples. As Muslims, they are opposed to the destruction of true embryos. So Zhang and his team took another approach called spindle nuclear transfer. So he took a nuclear from one of the mothers and inserted it into the donor's egg. The resulting egg, which had a nuclear from the mother and the mitochondrial DNA from the donor, was then fertilized with the father's sperm. So they used this egg to form an embryo, which was then implanted into the mother. And after 9 months, the child was born. Later techniques are approved in the USA. So Zhang and his team went to Mexico, where he says there are no rules. He is adamant that he made the right choice. To save lives is ethical thing to do, he added. So, what opinion do you have? What do you think? Is it alright or is it okay to call such children 3-parent babies? Leave your comment in the comment section. As always, stay happy and stay safe. Thank you.